In this video, I'm going to talk a little bit more about nested quantifiers, their order, and interpreting statements involving quantifiers and predicates. So this example that I'm going to start with is from the quiz that you should have been working on D2L. So I'm just going to go through and talk you through a couple of these statements, and then also talk you through a few of the questions on your homework for week 2 in the hopes that you better understand these statements involving quantifiers and predicates. So this first predicate that we're dealing with on the quiz, we've got the predicate t of xy. So anytime you're dealing with a predicate, it's important that you understand the domain of any variables being used. So the domain of x is, let's see, students. So we've got all students in, I don't know, at DSU, okay? And domain of y is all courses. So all courses at DSU. So just to get a feel for what that predicate means, we could say T of John Math 201, this would mean that, well, this could either be true or false, right? Remember, a predicate, you have some input, but the output is a truth value, okay? But the way that you would interpret this as a statement would just be that John is taking Math 201. So once you have an understanding of the predicate, then you can start adding quantifiers to see how that predicate, the meaning of the predicate, changes. So this first example, we've got there exists and for all. So before you do too much interpretation, I think it's important just to write down exactly what that means, symbol by symbol, and then try to go from there. So I'm just interpreting every single, so that backwards E means there exists, and then X is students, so there exists, or no, excuse me, we've got Y, which is courses, or course, right? For all, X, which are students, such that it is not the case that the student, or the course, right, is not the case that the student is taking the course. So the order of these nested quantifiers matters, okay? So this would mean something different if I were to write for all y there exists x, okay? So be careful with that. So what this is going to do is you're going to start with a fixed course, okay? So this is saying for some fixed course, for any student that I choose, it's not going to be true that the student is taking that course. Okay, now let's think about the statements we have to choose from. So there's a course that no students are taking. No course is being taken by all students. Some students are taking no courses. And so I'm thinking it's the second one here, because if I read this again, I say, okay, there's some course such that if I take all students, it's not true that all students are taking it. But what I'm going to do, and this will be handy when you're dealing with negation of quantifiers and nested quantifiers, if you manipulate the placement of this negation, it might help you better understand this statement. Because I think it's easier to start out with, it is not the case that some quantifiers predicate. Instead of having that negation in front of the predicate, let's try to put it out in front of the quantifier. So what I'm going to do is use those laws of negation for quantifiers. So remember, if I negate a there exist, it changes to a for all x. It's not the case that p of x is true. And if I negate a for all x, p of x, it changes to a there exists x, negation of p of x. But remember, these laws work in either direction, so I can start with the negation on the outside and push it on to the predicate, or I could start with the negation on the predicate and push it out. Okay, so this is the direction I'm going to be applying this law to manipulate this statement here. So we're going to start with there exists courses for all students such that it's not the case that the student is taking the course. So I'm going to pull this out bit by bit. So if I pull that out, that for all is going to change to a there exists, and then the negation is no longer in front of the predicate. Okay? And if you're not convinced, okay, start here and try to get here. You'll see that they're equal. Okay? And then I'm going to do that process one more time, pull that negation out in front of there exist, and that'll become a for all y there exists x such that t of xy. And so now let's try this again. So what we did here, let's try it again here. So this is saying it is not the case that, right, so that's that negation part, that for all courses there exists a student such that the student is taking that course. So it is not the case that if I choose any course, there's a student in that course. And so this makes me suspect this first one. There's a course that no students are taking. So let's go back to this interpretation here. There exists a course such that for all students, it is not the case that the student is taking the course. So now I can see that that interpretation makes sense for this statement too. And if you're not convinced, write down both of these interpretations. So write down there exists a course such that for all students, the student is not taking the course. So I'm convinced that number 7 should be matched to there is a course that no students are taking. But let's just take a look at these two different interpretations one more time to try to convince ourselves. So when I look at this symbolic representation, I think, okay, pick a course. If I run through all of my students, it's always going to be false that the student is taking that course. Okay, so there is some course for all students such that it is not the case that that student is taking the course. Okay, now let's look at this other interpretation. So it is not the case that for all courses there exists a student taking the course. Aha! So hopefully you can see that this first one should match to 7. So this would be 7 or 1, I think is what you choose. So now let's go to 8. And another strategy here is to start with the English statement and try to write it symbolically, okay? So let's go on to this next one. So what I'm going to do, so let's go on to the next one. We've got the negation of for all students there exists the course such that the student is taking the course. So And with negations, it sometimes helps too if you just interpret it without the negation. So we're trying to think about the statement, the negation of for all x there exists y t of xy. Okay, so let's write down what the statement means in terms of the domain of x and y, and then also the predicate t of xy. So let's go ahead and say it is not the case. And this is not clearly written, right? I think after you get it to this form where you're translating each part bit by bit, you can take it a step further and make it more clear as to what the meaning is, and that's what these options are doing here, making it more clear. Just like on the last one, right? It's a lot easier to read there's a course that no students are taking than there exists y course for all x, blah, 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 right? So let's look at this. It is not the case that for all students there exists a course they are taking. The student is taking. So this tells me that there are some students who aren't taking courses. Okay? There exists a course the student is not taking. And just like we did on the last one, let's go ahead and look at this with the negation in a different place just to see if we still get that same meaning, just to double check ourselves and make sure that we're on the right track. So if I negate a for all, it becomes a there exists, and then I negate what's ever left inside there. And then if I negate a there exists, it becomes a for all. So there exists a student for all courses. It is not the case that the student is taking the course. So yeah, this still makes sense. If I read this, it says, okay, I can pick a student. If I go through every single course, T of that student in every single course is going to be false. Okay? So because for this to be a true statement, because of this negation and the for all, this always has to be false for every course that I plug in. So I find a student, loop through all my courses, and for each of those courses that I check with the student, they're never taking it, right? So whichever way is more clear to you, hopefully you can see that these statements mean that some students are taking no courses. So there exists a student such that for all courses that student is not taking any of those courses. So I'm going to say this last one is 8. Okay. Now let's try number 9. And hopefully you're noticing here that especially looking at 9 and 7, they look really similar, right? With the placement of the negation. So hopefully you can see that they're going to mean something totally different. So you have to change that quantifier if you negate it. Otherwise it doesn't make sense, okay? So let's look at, let me erase some of this stuff, and let's look at the negation of there exists a course for all students such that the student is taking that course. So I'm going to start with just interpreting this without manipulating that negation. But so if I start there, I'll say it is not the case that there exists a course for all students such that all students are taking that course. And I feel like that statement aligns well with the middle statement there. But let's go ahead and try to move that negation around to see if our conclusion still makes sense. So if I negate a there exists, it becomes a for all. And then I push that negation into the next part, moving left to right. So negate a for all becomes, or negate a there exists, it becomes a for all. Negation of for all will become a there exists. So for all courses, there exists a student not taking that course. Okay, so this is saying pick any course. I'll always be able to find a student that makes T of xy false. Okay, so for all courses there exists a student not taking that course. So hopefully it's clear that this middle one should be 9. Okay, now let's check out a couple more examples to help you with quantifiers. So this is number 7 from week 2 homework, and this was a question that was asked at the session on Monday night, and so I just wanted to kind of reiterate what we had talked about for those of you who were not there. So because I wasn't able to make a recording, so we'll talk over these 3 questions because they came up that night. So this number 7 can take a little bit of time to understand versus what we just talked about, because we don't have a domain that we can visualize and fully understand like students in courses. We've got a domain just containing 3 elements, 1, 2, and 3. Okay, so the predicate doesn't really have much meaning to us. It's just we plug in 1, 2, or 3 into 2 variables and we get a truth value out. So we know what the truth value is for all 9 possibilities of inputs of x and y. So I know that the following predicates are true based on the information I've given. I know P of 1, 3 is true, P of 2, 1 is true, P of 2, 2 is true, P of 3, 1 is true, P of 3, 2 is true. Okay, so let's see, I've got 5 true statements. That means I must have 4 false statements. And so I have to list any predicates that weren't here, okay? Because it says P of xy is false otherwise, so I want to make sure I understand which ones were false. So P of 1, 1 must be false. P of 1, 2 must be false. P of 2, 3 must be false, and looks like P of 3, 3 would be false. So I've got 9, so I've listed all my possible inputs for this predicate. So I'm going to leave A up to you. I will say there's a lot of counterexamples here, but I could say P of 3, 3 here, and that would be a justification for a conclusion. But what I'm looking for on this question is I want to know, is it true or false, and then I want to be given justification for that. So I'm going to go ahead and do B completely, give you a hint on C. Okay, so and what I want you to see here is that these truth values are not necessarily the same, so the order of these quantifiers is important. So this first one, I'm going to start by writing it out word for word so I can better understand this statement with the nested quantifiers. So this is saying there exists an x such that, or an x for all y, such that P of xy is true. Okay, so it says such that. Okay, so when I read this, I think, okay, I'm going to have to pick exactly one or more, right? But for sure at least one. I'm going to have to pick an x. So 1, 2, or 3. If I plug in any y, if this statement is true, then P of that specific x and any y should be true. So since we have a finite, easily accessible number in our domain, we can just check with every x to see if it works out. So let's see if it works for x equals 1. So if it works for x of 1, then P of x equal 1 and any y should be true. But if I look at P of 1, 1 and P of 1, 2, it's not true. So I know because P of 1, 1 is false, I need to try another x. Try other x. The statement still might be true because we only need one x to satisfy this condition. Let's try another one. Let's try x equals 2. Okay. Well, P of 2, 3 is false. So that x won't work. P of 2, 3 is false, so try another one. Try again. Okay, and if it doesn't work for x equals 3, we're done, right? So if I plug in x equals 3, I've got p of 3. 3 is false. So that value for x doesn't work to satisfy the condition. So because of these 3 combined examples, I know that this is a false statement. Okay. Now, I want you to think about C for a minute, okay? This is saying for all x, there is some y that makes this predicate true. Okay? And so I'm going to tell you, I'm going to give you a hint, this is true, but to show that it's proved, you have to show that this works for every x. So you have to find a y for 1, a y for 2, and a y for 3. Okay, so to show that it's true, you're going to have to justify it, just like we justified it on B. You can write it a little nicer there, but hopefully that helps on that problem. Okay, and let me do, I think I'll do B. I'll do B for the negation here, okay? So if I want to negate a for all, and I want that negation to be right in front of the predicate as it is with that f of x, okay? So if I negate a for all, it becomes a there exists, and then that negation gets pushed closer to that logical statement. If I negate an or, it becomes an and. And I negate the second piece. And using double negation, I've got there exists an x, f of x, and negation of a of x. Okay? So if you have questions on that one, notice this order of quantifiers is really important. Okay, if I didn't have anything here on this quantifier, it wouldn't really make sense unless I put parentheses around p of xy and q of xy. So notice how they've gotten quantifiers right in front of the predicates on both pieces, or they've grouped that logical statement involving the variable in question and put the quantifier out in front. Let me talk about C here, and to try to help you with this one. And if you need more help and direction or a hint, just let me know, okay? So we've got 2 variables here, and our domain for both are integers. The domain for both is integers. So if I think about integers, they're just whole numbers with negative numbers included. So I've got -3, -2, -1, 0, 1. So they're all real numbers. It's a subset of the real numbers, subset of the rational numbers. Okay. So let's look at C. So first thing I'm going to do when I see anything with quantifiers is just write it out bit by bit and try to piece it together. So for all integers x, for all integers y, x times y is greater than or equal to x. Okay, now anytime I'm thinking about greater than, like what's happening here with this statement is I'm taking some number, I'm multiplying it by another integer, and I'm saying that it's always greater than the original integer or equal to. Now if we're dealing with positive integers, this would actually be true, and you could post on some discussion boards and to talk about that. But since we've got negative numbers included too, it's not actually true because it has to hold for any x and y that I choose. So for example, all you need to disprove something is just one counterexample, but it helps if you plug in a few values for x and y to better understand the statement that you're given. If you don't understand the statement, if you understand the statement, then just go with your counterexample. But what I'm going to do is say, okay, what if x is 2 and y is -1? So x times y is going to be -2, and x is 2, but x times y would not be greater than or equal to x then, because -2 is less than 2, right? So this counterexample shows that it's not true. However, you got to be careful before jumping to the conclusion that something's true, because if I would choose x equals 2 and y equals 3, x times y is going to be 6, and x is 2, and 6 is greater than or equal to 2. So in this case, it's a true statement for these specific values, but it doesn't work for any integers x and y that I choose. Okay, so I hope that helps a little bit with quantifiers. I think make sure that you're recognizing that the order of those quantifiers matters, the order of the variables with the quantifiers matters, and make sure that you understand how to negate quantifiers. I think we're going to talk a little more about common sets that we'll use, and then just let me know. We're moving back the homework due date for week 2, Thursday or Friday. I'll post about that tonight. So talk soon. Thank you.